Next is laboratory based testing. So this laboratory based testing methods are of two types. They can be electrochemical testing and they can be physical and chemical testing. So in electrochemical testing, usually you have different types of polarizations and impedance measurements. A three electrode system is used where you have working electrode, reference electrode and counter electrode. Reference electrode may be silver chloride or calomel electrode depending on the laboratory that is doing. They will use a potentiostat where you have volts, voltage and amperes as well. Now here you have the reference and working reference electrode to measure the potential and the counter electrode to complete the circuit when you're applying a current. So basically what we do is we apply a current and we measure the potential, that is measure the flow of the current that is happening. So this is how a potentiostat usually looks, and the connections are particular to the three types of electrodes. Electrochemical testing, usually this is a potential dynamic polarization plot. So electrochemical testing means that you have a plot, Evans diagram, you remember, that is potential versus current density. Now when you're doing electrochemical testing, you only measure considering Fe. So what you're going to get is this connected part, only the internal part, which is called the Tafel plot. What we basically do is we increase the potential from a low to a high and we measure the corresponding current density. So you'll get a plot which looks something like this. That is called the Tafel polarization. You can also do a linear polarization using the applied method. So in the previous case you had this kind of Tafel polarization, and you can find out the I core and E core values by putting tangents over here. So this details of this are given in the course of electrochemical polarization testing that is coming soon, and you can check out that course as well if you need to see how to fit these curves as well. So in this case you had logarithm of current density. Instead of that, here you only have the current density, and that will change the shape of the plot, which is called the linear polarization resistance. So you apply a potential and you plot the current density. The slope of this small part, which is between plus minus 50 millivolt, because in this case it is in this range it is linear, in that slope will give you the polarization resistance. So now you can calculate the corrosion current density, polarization resistance, and the beta A and beta C, which are the slopes of these anodic and cathodic branches. So you even if you don't do this test, you can still calculate the polarization resistance from the previous values as well. The next is calculation of corrosion rate. So this is a typical coupon test method where you insert the coupon inside and you apply it in this coupon test. You apply it to the you see how much weight that coupon has lost. Then you give that weight loss in grams, and you find the area of that coupon exposed to get the final MPY, that is mils per year. Alternatively, you can use the corrosion current density found in previous case and multiply it with the equivalent weight and divide it with density to get the similar corrosion rate. So the factors of 0.13 will change depending on what unit you're using. Thus when you're trying to check if the corrosion in the pipelines or reactors, how it's happening, or whether you want to analyze how much the corroded part uh, has got corroded, or what are its electrochemical properties, these three tests are really important. The next is electrochemical impedance spectroscopy. So this is similar to the previous case. You will still apply, you will still have a 3 electrode system. You will still apply a potential, but the potential will be sinusoidal. So and it will go to a maximum of 25 millivolts. So that's really small because we do not want to destroy the sample like in previous cases. So it will go high, positive and negative, and with respect to each part the current will be measured. So with respect to the first part point, you have a certain current measurement, and because you are using a alternating current, you have values of frequency which is done. So typically it's not done at a single frequency, it is done at a very high frequency first, then medium frequency, and then very low frequency. The impedance is in this case is calculated because it is alternating current. We do not really refer to as resistance, it is impedance, and it is calculated from the ratio of this current. The value that we get over here is actually given by the software itself, and there are two parts that occur in this case, the Nyquist plot and the Bode plot. So Bode is the Z versus frequency, and Nyquist is the imaginary Z. So they will resolve this impedance into real and imaginary parts using mathematical Euler's formula. So this Euler's formula will give us the imaginary and real part. So you can get two different plots. If you have a good coating, the shape of the plot will be a straight line in ideal situations. As the coating starts degrading, it will start going into arcs and then into ideal semicircles. If you have some kind of diffusion or Warburg's impedance, then you may have a different area. If you have a metal corrosion happening, that you may have another semicircle. So that way you have different shapes, but because this is a non-destructive testing, you can actually do it on the existing structures as well, and over a period of time. So after every month or every 2 months, and if you have a coating, then you can do it on the coating as well, so that you can see how the coating degrades for the pipelines over a long period of time. That is a speciality of the EIS technique. The next is stress corrosion cracking. So stress corrosion cracking is test is different because it consists of a proofing. So we are basically loading a tensile sample over here and over here, and we are going to turn this screw to to pull it up. So we are going to load it to a constant predefined load. Then we can these component this electrolyte is filled. So if you're testing for hydrogen sulfide stress corrosion cracking, you can fill it with solution contain, and you can give inlets for hydrogen gas. Sometimes these proofings are also connected to the 3 electrode system to measure the EIS as well over a period of time. So you can integrate some of the previous polarization tests with these kind of stress corrosion cracking tests to see how it is going to work, especially in case of oil and gas. This is a very common test that is used, and because there is a lot of stress corrosion cracking that is seen in this industry. So the next test type is the cyclic corrosion chamber. So cyclic corrosion chamber is a way to simulate the real environment. In the previous case, we saw that the only a single electrolyte medium was used, so we don't really know how it is going to work. But in usual cases, if you have a pipeline going through the desert regions or even in normal regions, you will have rainfall, then you'll have completely dry weather. So the coating and the pipeline in general is exposed to cyclic nature of temperature and humidity. These cyclic conditions can be replicated in this cyclic corrosion chamber. So you can put in panels of your steel that is used in the industry, the pipeline, and you can program it to get the cyclic nature. The corrosion that occurs on these will give you a more accurate picture of how the corrosion will occur. Then you can take these coupons and do the previous tests to see how their properties have degraded. And this is just an example of how the coating degradation will look over a period of time. So you have a scratch, and then over a period of time that scratch will the moisture will go inside the scratch. If your coating is good, nothing will happen to the coating. That way you can see after exactly where the corrosion is going to happen also. Physical and chemical testing usually includes looking at the morphologies of the coatings and also at how the chemistry of the coating has changed. So these are two examples from different coatings. This is a field joint epoxy coating, and you can actually see the scanning electron microscopy giving you the bubble. So you can go up to the scales. You can also see the fillers of calcium oxide and calcium carbonates and silicon dioxide inside the fillers as well. The chemical testing consists of Fourier transform infrared spectroscopy. So this is related to how the bonds in the epoxy will change. I have talked more about this in the science of coating section, and also that will be coming soon. So you can refer to that course if you want to go into a greater detail of how the Fourier transform infrared testing and the scanning electron microscopy works. So the use of this in oil and gas industry is that you can actually do a good failure analysis of the morphologies of the cracking as well. So even in this case, the cracking can be seen if you polish it in the cross section, and you can actually see which pit or what kind of pits have led to the cracking. In the FTI also there are a few other types as well. So in this case you can go to see if the coating has degraded. So is it because of the, so if your coating has degraded because of the UV rays or sunlight, the bonds that break will be different. If your coating has degraded due to rainfall, then the bonds that changes that are seen here are different. So that is one way of figuring out what it is that is causing the degradation of the coatings. These are special tests which are done and oil and gas industries, where you have the shore hardness test to test the hardness of the coating. You have the adhesion tester where you press this down, and there's a doily stuck over here. So when you press this down, this pump applies a pressure and this doily is pulled out. So if your coating is not that good, then the doily will pull off your coating. So whatever force is required to pull off your coating, that is recorded in this system. The next is the thickness tester. So you have electromagnetic induction thickness testers which you keep on the top, and they are calibrated to the different thicknesses of the pipeline. So you can test what thickness is there on the pipeline or what was there previous. Holiday tester basically works on the principle of electrical circuit. So if your coating is completely intact, then the holiday tester will not complete the circuit. If it has a defect, then that current will flow and the circuit will be completed. So you will see some kind of a beep or resistance value over here. This is also a holiday tester, but it is a wet sponge tester. That's the only difference. And the voltage applied will be low. So here the sponge will be wet to ensure a good electrical connection, and you can directly do an internal holiday testing.